All right. So now we have this kind of set up. I'll give you a little walk around on how this would correspond and what I was saying about angles and the importance of geometry. A lot of people don't quite understand this stuff. These are basically the same thing. This will just show you an arc. But they'll still line up the same angles in degrees and such. See? 90 degrees is still 90 degrees. So, geometry works. So what I've done here is trying to give you an illustration. Like, this device used to work a lot better when I first built it years and years and years ago. It's been neglected, but now it's just to kind of show you what my idea is. I'm not going to tell you what I seen through it. It's missing I had a skateboard. You sit on a skateboard. You can't just stand on the ground. You need an inertial frame of reference, and you need a static frame of reference. Okay, so what I've done is I set this plumb, which would be going to the center of gravity, aka the Earth, right? The center of a sphere. And then I'll set the angle, the complementary angle, to your latitude. And then you want to do is you want to have this kind of squared up in line with your longitude, because you need to have, you can't just point it like, well, since this is just kind of free floating here, it's just an idea to kind of show you. This line here, right, is be the great circle route of your latitude. So these angles are important. So this right here, see, I thought that had peg. Sorry, let's try again. Nope. Okay. This is essentially this bottom portion of this tool. Let's see if we can see inside here. It's so rusty and oh man, it took me forever to make this. I made it out of wood, you know, because like the ancients, they didn't have CNC machines. They didn't have any type of AutoCAD or anything. So I had to make my own little gear. But see how this gear is straight. So this gear represents a segment of a great circle route gear around your spherical Earth. This one here is a gear. It's much smaller, maybe, I don't know what, 12, yeah, about 12, 13 inches in diameter. Okay. Now, if you want to try to work out the ratio between this and this, you have to come with a presupposition that this straight line is actually a circle. You can do that if you want to. That's just a waste of time, because we're trying to make an observation and see what we get from it, not re-edify or try to prove what we think we already know. We want to get raw data. We want to get some information, not what people's incredulous beliefs are and stuff like that. Okay, so after you set this up, and I'll show you again after I'm done with this, with the camera that I talked about when I originally contacted you and all those things. So this gear, a gear against a gear, they both cannot rotate the same direction. And what I mean by that, I think you already kind of know, because you sound like you might have some kind of information. See my fingers? You see my fingers? Okay, a rotating gear has to rotate like this. So this is going clockwise, this one's going counterclockwise. They can't both go like that and have a gear work. That's just not how gears work. It's mechanical. It's not someone's opinion. Okay, now this gear, if this is a portion of the Earth and it's moving due east, right? This gear, if we can situate this gear to where it does not move, this gear has to rotate in the opposite direction. That's just a fundamental principle of mechanics. Now, what I've done here, to make this, you have to set it, okay? It's been a long time since I messed with this, a lot of years. Now you set it at a particular, like so it can move this way. See, it's so freaking rusty, it can't even really rotate as good. And the wood got all swollen, look how dirty that got. Yeah, so this gear will move across that other gear, the grooves. These will absolutely work. Now, this portion, what I've done, I have the center of this gear, so it rotates around a pivot, like a center point pivot, not just any pivot, because that doesn't qualify as all absolute pivots. This is a center point pivot, and this one here is an offset pivot. Now, this one will go around this one, but this one will go around, but at one point. Now, if, kind of fast forward here instead of trying to educate you in these principles, but if this can pivot on its own, see? It can pivot around this point, and it can pivot around this point. It can pivot in an oblong action, like it's got to make like a intersecting line across that center bolt, right? Just the same way a train tires work, those old steam powered trains. This would push around that, causing this to move around the immovable ground, because we know that trains don't outweigh the ground, and it will cause the train to move forward. Same exact principle. See, this piece of junk, so dang rusty. See what happens when people, yeah, see, it goes around because it's mechanical. It has to. It's not an opinion. Okay, now, if I look down this pipe that I attached here, what I used to do, I've done this observation. I'm not going to tell you what I saw and how things are. You can build your own. Go test it out. I hope everyone does, because don't take my word for anything unless I tell you that I love you. But that being said, go figure this stuff out on your own. So you have your own merit, you have your own life, and you can live, because life is beautiful. I mean, look at all this beautiful stuff out here. Anyway, so you look down this tube here. See this? That'd be the same as your telescope, right? This doesn't work, does it? Nope. See those two circles? Oh, so we need 2 points. Make a straight line segment. Shortest distance between 2 points. Okay. Now, if you're standing on the ground, well, now I'm attached to this, which is attached to this. This is attached to this, attached to the ground, and as I'm standing on the ground, I am also attached. So this cannot work. So I have to, what? Be on something that can move independent of this gear piece, this great route gear. I do not have that no more. Sorry. But as you look down this tube, now, if an object, you can't see the moon in my junky camera, but it's beautiful up there. And if you really want to get into astrology, you'll find that, what is it, Venus and Jupiter, they're right about here tonight. They're almost going to kiss. They're pretty close. But here we go. So you look down this tube, and if the object outside of these points, if that object is moving, well, you would have to move this tube around this point to keep that crosshair, let's say the sun, on the sun or on a star. You would have to move the pipe. You would have to physically move. You'd have to move in its place like this. Now, if it's stationary, you'll say the sun is stationary or the star is stationary or whatever you're looking at through the pipe is stationary, and the ground that this gear is moving on, okay, what would happen is this would stay fixed like a solid bar, just the same as a train track, a train driving wheel. And what would happen was, because you're holding this fixed in place, right? The wheel will move. See? I'm not moving its place in space, but the wheel's moving around it. This is a principle of mechanics. Now, this is a piece of junk, and it's going to go to the trash. But back in my good old days, this is a device, and I built it, and I tested it, and I proofed it. So by that I mean I've taken this thing and I've tested it in 2 applications. One, if you don't agree or whatever, I mean, maybe you do, maybe you don't, I don't know. But this is stuff that people don't ever do. People are lazy. People eat too much sugar. They watch too much Nintendo and Facebook and all that crap. This, if you have any inkling behind why this would not work, I would like to hear it. But build one for yourself. Maybe you have access to a machine shop and you can have them mill it out of aluminum or hardened steel, I don't know. And then test it. Have your friend drive your truck, put this up in your truck, hold this through the thing like this, point it as something you know doesn't move, like let's say the top of that mountain over there. And as the truck moves, see what happens. And then have him park the truck and have him, come with like his hand or like a stick with a carrot on the end and dangle it in front of your face, and then have him move the carrot across the truck that you're stationed in and see what happens. You can test those 2 different things. It's not someone's opinion. You can absolutely make a thing. Everyone can make stuff. Like, just do it, It's not that hard. What I found is that somehow our conversation has become into like the very thing I didn't want to go into, which is just, it could be. We can speculate, we can draw, and we can mathematically calculate all these things. And it's not the same as the reality. So as a point of proof, okay, if I have, this is why mathematics don't work, and this is why Nikola Tesla was explaining that you're wandering through equation after equation, but none of it applies to reality. You need something testable, right? Demonstrate your science. Don't just tell me that 2 parallel lines will intersect eventually. That's horseshit. Okay, what I have here, if I take three of these sockets, okay, I have 3 sockets. Well, 3 sockets plus 2 sockets. Now I have 5 sockets. That's math. That's true. In the real world, look, there's 5 sockets. Now if I said 3 sockets minus, let's say 5. Well, if I take 3 away, right, I still don't have more to take away. So you can't have math be reality because there's nothing more to take away here. It doesn't really apply. Math is it's not physical. But you could argue a metaphorical point and say, well, I have more than 3, I have more than 5, I have, look at all these sockets. In any case, that's my point about actually demonstrating your claim. 2 intersecting lines, right? They are non-parallel. That is impossible. That is absolutely impossible. Because that defeats the point of even claiming that they're parallel in the beginning. Now, fast forward, go back, forth. I'll leave these videos up a little longer. I mean, may I'll leave them up indefinitely, but try it, man. Like, look into this, find the flaws, do the thing. I mean, this is 90 degrees. Look. There's one more angle I didn't tell you about. I keep forgetting this one. Okay, so we'll set this up, the complementary angle. So this complementary angle is just parallel, right? It's a parallel line to the axis of Earth. Now, from that axis, I need to rotate 90 degrees. See, I'll put this on here at 90 degrees. See, it's not see this thing? It's all rocky. So down here, 90 degrees. So it's 90 degrees. And then when you set that camera up, it needs to have those angles. Now, I'm going to do one more little video for you before I go back to the drawing board and start biting. That's funny. But by that, I mean actually drawing pictures. I'm going to set these angles, and I'm going to set a little camera on there just to see what it looks like. So for the star trail picture, because I've personally never done those angles. Well, I've done those angles, but not the camera. I can't make the star trail picture, but there we go. Now, that's my last. That's the last flat Earth tool I built, and if you're still watching this after this amount of time, prove me wrong. Prove that find the flaws. And it's funny because I'll make another drawing from this video, just to have more information in there for you. Leon Foucault or whatever, I don't speak French. The idea of the Foucault pendulum, that doesn't apply at all. And I'll show you in a drawing, and you can use it if you want, or try to figure out how it would magically work. But you require for the Foucault pendulum, right? Here's a pendulum. Well, I use what's called a plumb bob, but it's the same concept, okay? You see this? No, it's not one of those stupid magical crystals that these people will get all weird about. Now, if this is at rest, okay, it will never start swinging if it's at rest. I have to act on it. Action, reaction, equal and opposite reaction. Now, if I were to say that this thing is going in a straight line in any direction, back and forth around itself in its own swinging, and you were to say that the ground was going around it like the Foucault pendulum, and as the ground moves, it knocks down a domino. The ground moves, it knocks down a domino. The ground moves, knocks down a domino. See, the problem is that this is physically attached to me. I'm holding it, my arm, my feet, they're sitting on the ground. So the ground would have to go around in a circle like this at my latitude, 37 degrees north. For any Foucault pendulum to work, it has to be inside of its swing arc at its latitude. So it would have to be exactly north or exactly south. Because if this is going in a straight line, the ground has to be perpendicular to it. Well, not perpendicular, because that has to be adjacently moving to this action. I'm going to tell you, the ground doesn't move in any, well, it moves like it's moving like expansion and contraction, because look, the snow made all this stuff heave. The ground is like pumped up. It's like it's heaving right now. So I would agree that entropy does absolutely cause things to move in the sense of moving, because one high pressure will go to another lower pressure. But anyway, I'll do one more for the camera, and I'd love to have your input. You sound like you're open, like you're not like you're not very whatever. I don't know a word for it. But yeah, what do you think, man? What do you think of my country? How beautiful this place is. You've been getting a lot of snow, so it's good for water values. But I don't want to work in it. Okay, now the final tool, but not the final point. We have the same principle of the complementary angles. We understand geometry. The Earth was this way. We'd have a 90 degree here. At the center, in two axes, we know that north, 37 degrees north, would be this line, right? So from this line, we can do what? Instead of complementary angles, be parallel. See? It all happens again. Be parallel with the Earth's axis. From this parallel line, we just go 90 degrees. See? 90 degrees, and we'll be parallel with the rotation. This is going around the axis, right? So that final tool is the same principle. But what happens is on the surface here, you're making the one tiny little segment of gear cross like this. We don't even need to go for a whole hour to get 15 degrees. This is nonsense. We just need movement. So we have the smaller portion of that device, which is just a straight portion of a great route around. See? I'm just taking a smaller portion around the pole, and the other portion is the wheel part, right? Is the wheel part, so it has to move somewhere across that bigger gear. Now the other part is the tube that makes the observation. You're going to hold it solid, and what happens here, oh man, this thing's a piece of shit board. Look how dirty that is. It looks like Phoenician plaster. Phoenician plaster. That's what it looks like. Okay, so on the subject that we have the wheel moving across the other wheel. So why that would happen is because if I have, like on a train, right? If I have a point here and a point here, and I have something causing this to be solid, this is how the trains look. This little knuckle will rotate inside of there. When the engines go off, they're like big steam engines, right? Expansion drives this cylinder, and because this is offset of the center, it gets pushed around the center point, because this is a solid connection. Now, this portion of the train right? This portion of the train is independent of the track. And that's what allows it to move forward. So in my little tooling thing, wow, this is a junky ass whiteboard. Look at that. Oh man. Ah, cheap crap from the dollar store. Okay. The only argument that would ever arise that I found for that last tool is because they're all moving in sync. So let's say that the Earth is so big, right? So big that the wheel and the segment of wheel and the observation, right? They're all moving in the same frame of reference. But the only problem with that is that I feel I have solved is that you sit here right, and you look through this thing, but you're on a separate moving platform, a skateboard. So if the ground is moving, you're also moving in the opposite direction. There's no force causing you to move with this. You're trying to hold this position to something that's fixed. It in turn will translate into these wheels moving this way, because you're holding this solid. So the thing that you're looking at is stationary. This wheel, right, is going to go, it's going to move. It's going to roll. Now, if this object is moving, this has to be sitting on a fixed platform, and the star moves. That means that the ground, the skateboard, the post, this segment of gear is stationary. But because something's happening, you're going to move, and you're going to cause this to rotate and look at the star or sun as it goes past. And you can test this. You can put this in a moving object. Don't drive it north to east. Don't drive it south. Shit. Don't drive the truck. Put this in your truck. Have your friend drive your truck. Have that telescope, the little metal pipe that I have on there, trained on something, on a mountain, or something you know is not moving at the rate you're moving. But go north to south, or south to north. So the rotation has no implications. And then drive and see what it does. And then have your friend move an object across the apparatus and see what happens. Because they can't have two same outcomes. Because they're two different things. So, that's what that is. I don't know why this board got... Look at this. This board is so... Oh, what a pile of junk. Look at that. I can't even get it clean. Okay, now I'm going to do one more, and then I'm going to go to bed.